So in this lecture, we will be going over the remaining parts of the interrupts. So we will be looking at the interrupt numbers, how we can enable interrupts, and how do we control the interrupts using the registers. And then we will be looking at the CMSIS interrupt functions in this lecture. So in order to refer to our interrupts, we need to have a unique number. So this unique number is called interrupt number, or it is in short IRQ. So if you look at the vector table, we have all these addresses, and these addresses actually for the processor exceptions, and the vector numbers are from 0 to 15. And starting from vector number 16, we can have external interrupts. For example, IRQ0 is an interrupt for the port A. IRQ1 is an interrupt for port B. Similarly, these interrupt numbers will continue, and as you know, we can have up to 240 external interrupts, and each of these interrupts has an interrupt number. And we will be using these interrupt numbers in our functions to refer to the specific interrupts. So these interrupt numbers are listed in this header file for the Launchpad, right? If you look at this .h header file, you will see there is a section called interrupt number definition, and in the first section we have exceptions, the processor exceptions. These are the 16 of them, and then the remaining ones are the specific interrupt numbers. So the first part is defined by ARM, but the interrupt section, actually these are defined by the chip vendors. So every chip vendor might have different interrupt numbers. For example, Launchpad interrupt numbers might be different than the ST Microelectronics interrupt numbers. Okay, so here, as you see, interrupt number 0 is defined for the GPIO interrupt, and then 7 is defined for the SSI interrupt, and 8 is defined for the I2C interrupt. And for UART 0 and UART 1, we have interrupt number 5 and 6. Okay, so these interrupt numbers are used, as I said, it is used in our functions, and these functions are defined actually in this CMSIS library. Okay, so this library is already ready for you to use, and in this library we will see more details on this library. There are some functions, register definitions, etc. So as we learned from the vector table, the first 16 exceptions are defined by ARM, and these are processor exceptions. And then we have 240 peripheral interrupts, right? And these peripheral interrupts start with number 0, interrupt number 0, and they are assigned for this for the peripherals such as timers, ADCs, UARTs, or any other modules. And these are defined by the chip manufacturers. So these interrupt numbers are important for us, but in our program status register, as we know, we have 3 parts for our program status register. One is application program status register, another one is the interrupt PSR, and the third one is execution PSR. And if we combine them, then we will have this program status register, and here what is important for us in this lecture is the interrupt service routine number, ISR number. So when we are executing an ISR or interrupt, the processor will put the ISR number on this register, but this ISR number is different than the interrupt number. So this is a 8-bit field, and it is range from 0 to 255. But when we put this ISR number to the this PSR register, what we do actually, or what the processor does, it takes this interrupt number and adds 16 to it, and it puts it here. So all these numbers are positive here, ISR numbers. So the ISR number is different than our interrupt number. Okay, so just note that the processor adds 16 to it, and then it will put that number into this register while the processor is executing an interrupt. So how do we enable an interrupt, right? As we learned, we have this nested vectored interrupt controller which handles all our interrupt processing, and we have our peripherals. So this peripheral will request an interrupt, it will send its request to this NVIC, and then this NVIC will handle this request, and then it will let the processor knows there's an interrupt request, and it will let the processor execute our interrupt. So there are mainly two steps. We need to program the peripheral control register to allow it to generate interrupts, right? So there's a control register for this peripheral, and through that register we can enable the interrupt for this peripheral, or we can disable it. And then there is also some register in the NVIC that we need to configure so that we can control the interrupts, and we will see these shortly. So basically each peripheral has an enable bit for the interrupt, and it's a flag bit saying that it needs interrupt to be executed, and there's a flag bit for each interrupt. In the execution core or the processor core, we have these prime, mask, and base PRI registers that also enables all the interrupts, and also it gives the level of the interrupts that can be executed using this base PRI register. So basically, to enable an interrupt, we need to set some registers, right? So we need to configure some registers, and then after we configure the registers, we can execute our interrupts. So basically, in this interrupt processing, we need to learn about these registers, and also we need to learn how to set and clear these registers. So for that, we will be using some functions, interrupt functions from this CNSys library. Okay, and we will be learning about those as well. Okay, let's look at ARM Cortex-M interrupts. As we said, so each potential interrupt source has a separate enable bit, or we call it ARM bit as well. So this ARM means enable, arming, right? Okay, so for example, for this SysTick control register, we have this interrupt enable bit. So this is the enable bit, interrupt enable bit for the SysTick control or the SysTick module, right? So this is called ARM bit, which is bit 1 in this register. So you can set this bit so that you will be enabling this module, or whatever the module it has, to accept interrupts. So you can deactivate this field so that no interrupts will be allowed from that source. So also each potential interrupt source has a separate flag bit. So in this case, bit 16 is the flag bit for this SysTick a control register. So whenever the flag bit is 1, it means the SysTick is asking for an interrupt to be executed. So hardware sets this flag when it wishes to request an interrupt, and after executing the interrupt service routine, the software will clear the speed field to signify or to show that it has already completed or executed this request. And then, so we enabled the source, interrupt source, but we also enable the prime mask in the processor, because this is the global register that controls all the interrupts. So then we need to set this prime mask I bit to be 1, and then we also need to set the priority level of the allowed interrupts. So if we set base PRI to 0, it means we will be executing all interrupts. But if we set to this 5, it means we can only execute interrupts with the priorities are higher than this 5. And in Cortex-M, higher priority means lower interrupt number, right? So if I set it to 5, I can only execute interrupts 0, 1, 2, interrupt numbers 0, 1, 2, 3, and 4, right? With the priorities from 0 to 4, I can execute them, but anything higher than 5 and higher, I cannot execute them. Okay, so this is the process where we set the enable bit in the source, and then we also need to set this prime mask register in the processor, and we also need to define the priority level for our processor. So basically we have 4 conditions for the interrupts to happen. We need to enable this global interrupt in the prime mask. So if we make it 0, it means we are enabling interrupts. So setting prime mask to be 0, we enable the interrupts, and as an instruction in the assembly we can just execute this instruction. So this instruction is the change processor state interrupt enable. So once we do this will be basically setting this prime mask to be 0, and it will enable all the interrupts. We can also use some function to enable the interrupts. So this is the _enable_IRQ, enable interrupt request. Okay, so to disable the interrupts, we need to set prime mask to be 1. So this needs to be 1 actually. So we can also use this _disable_IRQ function also to disable the interrupts, right? So these are the ways to enable the global interrupt or disable the interrupts. So another condition is, as we mentioned earlier, we need to enable the source or the source interrupt peripheral using this ARM bit, and we need to set it to be 1 to allow interrupts. And the third condition is we need to set the priority level, and then for this we need to use this NVIC priority register to set the interrupt level for the source, but for the processor also has this base PRI to set the interrupt level, right? Any priority level less than this will be executed actually. Otherwise, if this priority number is higher than this base PRI value, it will not be executed, right? So this tells us which interrupts can be executed. And the fourth condition is trigger, right? So if we all set this register accordingly, then we need to trigger the interrupt. So hardware sets source specific flag when it wishes to request an interrupt, right? So if there's an interrupt request, the hardware will set the corresponding flag bit in the register. So this way the hardware will tell the NVIC, okay, I have an interrupt to be executed. And after the processor executes the interrupt, it will clear this flag bit. So these are the 4 conditions for an interrupt to happen. So if there's an interrupt request, it is not always executed right away. So if the trigger is set but any other condition is not true, then the interrupt will be in the pending state, and it will wait until all the conditions are true in the what we have seen in the previous slide. So also, as we said, the software needs to acknowledge the interrupt. Otherwise, if you do not clear this flag bit, you will get endless interrupts, right? So the processor always will think that you need an interrupt. So once ISR is executed, this flag needs to be also at the end of the interrupt service routine, this flag needs to be cleared so that you will not get continuously interrupts. So now, how do we control these interrupt processes? We need to configure our registers, and then we can use our functions for this interrupt processing. So register, we need to learn about this interrupt enable registers, interrupt priority registers, and PRI-MASK and base PRI registers. So these are the registers that are related to the interrupt processing. And we also have some functions. These are provided by this CMSIS library. Okay, and we will learn about this shortly. So these functions, you can use them to enable interrupt and disable the interrupts. So another functions that you can use, the functions to set the priority level, and then we also need some functions to clear the pending status of an interrupt request. So let's look at the NVIC interrupt enable registers. So these enable registers are located in NVIC. So these are also called interrupt set enable register in CMSIS. Okay, so they both are the same thing. You can either use this name, ISER, or interrupt enable register. So this register defines a single bit for each interrupt source. So SysTick, actually this is a special module, so it does not need this enable step. So by writing 1 to this register, interrupt enable register, you enable the interrupt. If you are writing 0, it has no effect because this is only enabling the interrupt. So for disabling, we have another register. We have 1 register for the enabling, 1 register for the disabling. So we have separate register for enabling and disabling. For example, this NVIC enable 0 register or NVIC ISER register is located in this address. Okay, so this is the address for this register. And then this register defines the enable bits for this interrupt requests or IRQ interrupt numbers from 0 to 31. And we have another register for interrupt numbers from 32 to actually this will be 63, and it will continue. So we have more than actually 2 register enable registers, so we need to cover all the interrupt requests. So there could be enable 2, enable 3 registers for the. So in this table I only show 2 of them, but there are more enable registers. So for this address, we can define this address with this register name, and then in our code we can just enable, for example, interrupt number 1. If I write hex 02 to this enable 0 register, I will be enabling interrupt number 1, right? So if you write hex 1, you are enabling interrupt number 0. To enable interrupt number 1, you need to write hex 2 to this register. Okay, so there are, as I said, more than 2 enable registers. So these are from the data sheet. So it shows the address offset for these registers, enable registers, disable registers, and pending registers. So these are the address offsets, and this tells you it is readable and writable, all these registers, and at reset these are the initial values for these resets. So there are some other, I am not showing all the interrupt related registers, but there are other registers as well, such as interrupt clear enable register, interrupt set pending register, interrupt clear pending register, interrupt active bit register, and which is, this one is read only, and interrupt priority register. So there are more registers related to interrupts, but mainly we will be using this interrupt set enable register. And this table also shows you the addresses of these registers, and then as you see, it is from 0 to 7 to cover 256 interrupts, and you have 8 registers for each enable register or disable clear register, right? So these are the addresses for these registers. And if you look at the data sheets or from the user guides, you will see the address, name, type, and a description for all these registers. So we have seen these registers for the interrupt controller, and in this interrupt processing we also need to set the priority of an interrupt, right? As you might remember, for Cortex-M the interrupt priority has inverse relationship. Lower priority means higher urgency, right? It will be executed first, it means. So if a priority of an interrupt A is 5 and the priority of interrupt B is 2, B has a higher priority and than A, therefore B will be executed first, then A might be executed. So as we learned from the previous lecture, some priorities are fixed, and these are the for 3 interrupts: reset, hard fault, and non-maskable interrupt. Their priorities are fixed. So reset has the highest priority, and then the second highest priority is the non-maskable interrupt, and the hard fault is the next highest interrupt. But these are fixed, you cannot change these priorities, but the priorities for other interrupts you can change their priorities. For the other interrupt requests, their priorities are adjustable, or you can set it to different values. Okay, so this slide shows how the processor handles this priority. This is just shown for the exceptions, right, in the processor. So each exception source, these are fixed priority numbers, right? This could be programmable and other sources of exceptions. So processor basically at each state it will look at these priorities, and then it will find the minimum. If there is a request for these exceptions, it will look at these numbers and find the minimum, right? So this is the incoming exceptions. So this is the incoming request. So it will find the minimum. Also, it will find the minimum from from this section where it tells us the base level for our priority, right, which is set in this base PRI, and what is the priority of the current exception. The processor might be executed an exception, and it will also get this active exception number, and then it will find also the minimum of this section. So the incoming priorities with the current priorities, they will be compared. If the incoming priority is less than this EP number, which is coming from this execution priority, then it will be executed. Otherwise, if this number is higher than the value here, it will not be executed and it will be put on a pending state. And then these priority values are stored in this interrupt priority register. In short it says IP, interrupt priority register. Actually, each priority register has two fields. One is called preempt priority, the other one is called sub priority number, and it has 8 bits, but these 4 bits are not implemented. So the number of bits that you use in this priority byte is configurable, but in this example it is only showing 4 numbers that you are using. For this class, don't worry about this, what is the preemption priority or sub priority. So basically this section will define the priority level of our source. Okay, but know that there are different sections in the priority byte, and this part is not implemented, the first part, but only for these, the biggest 4 bits are used to define the priority level, but you do not need to learn the details about the preemption priority and sub priority. You can also look at this vector table, and then you can find the vector addresses of this. Actually, these are the vector addresses for our interrupt service routines, but there is also a NVIC register related to each interrupt, right? So if you like to set the priority of this GPIO port A interrupt, then you need to go to this NVIC priority 0 register, and then you need to use bits 7 to 5, 7, 6 and 5. You will be using actually 3 bits here. So for port B, GPIO port B, so again you need to go to this priority register 0, and then in this case you will be modifying bits 15, 14 and 13. So actually here it shows you what is the name of the priority register for your interrupt and which bit fields that you need to change for these interrupt handlers. So as we said, right, our peripherals have interrupt requests, right? So GPIO port A might request the processor to handle an interrupt. So, but for each interrupt request, we need to set the priority. And to set the priority, we need a register, right? So these NVIC priority registers, right? So we have this NVIC priority 0 register, priority 1 register, priority 2 register, 3 registers. So these are the name of the registers that we set the priority of these interrupt handlers. So these are interrupt handlers. So this is like a function, right? This is a C function, and this C function is on the memory. The address of this C function is here, right? So in the memory location is here, and the address of this actually function or interrupt handler will be written in this memory location. Okay, but when there's an interrupt request is happening, then we also need to tell the processor the priority of this interrupt request, and there is these bit fields. So as you see, this priority 0 register is actually controlling GPIO port A, B, C, and D. Okay, and then let's say I would like to set the priority of GPIO port A interrupt to be 7. Then I need to go to bits 7, 6, and 5 of this register, and I need to write 7 to these 3 locations. So let's say I would like to set priority of this GPIO port D to be 3. Right, then I will be going to this register, priority 0 register, and I will be writing 3 to this bit field, right, 31, 30, and 29. So these bit fields are holding the priority of this GPIO port D handler. So this is a little bit easier to understand from this table. It is also showing you the same thing, but in this case, register bit field 7 to 5, bit 7, bit 6, and bit 5 tells us, defines us the interrupt priority of this port A. So bit 15, 14, and 13 tells us the interrupt priority of port B, right? Similarly, if I would like to set the interrupt priority of this, let's say, Ethernet interrupt, right? To set the priority of this Ethernet interrupt, I need to go to this priority 10 register, and I will be changing the bits 23, 22, and 21, so that I will be setting the priority of the Ethernet interrupt. Okay, so this table shows you how you can define the priority of these interrupts for different modules. Okay, for example, to set the interrupt for the USB 0, then you need to modify bit 7 to 5 of this priority register 11. So you need to look at this table from the data sheet, and from the data sheet you know the bit fields, and then you modify the corresponding bit fields for your interrupt module that you are trying to set the priority. So higher order 3 bits of each byte define priorities. It has 8 bits here, but you are only using upper 3 bits. Okay, we are not using bit 4, 3, 2, 1, 0. And so this is the second byte, third byte, and fourth byte. But we are in each byte, you are only using high order 3 bits. And we also need to configure this prime mask register. So these are the special registers in the processor, right? One way of setting this prime mask is using this special instruction, move to special register MSR. So to write 1 to this prime mask, we first move number 1 to this register 0, and then this register 0 is written to this prime mask. To write 0 to prime mask, so this will enable all the interrupts, we first write to register, and from register we write to this prime mask. Okay, so this MSR only accepts registers, you cannot put number here. So we learned about setting the registers. In the priority registers we need to set the enable registers, right? So we also need to configure this prime mask and base PRI registers. So these are the special registers in the processor, right? These are the global enables for the interrupts. So to set prime mask, we will be using this special instruction MSR, right? And then if we are writing 1 to this prime mask, we need to first move 1 to R0, and then we will use this MSR instruction to write R0 to this prime mask. So MSR means move to special register. So this is the write instruction to prime mask. So if you would like to enable all the interrupts, then you need to write 0 to prime mask. So basically you will be moving this 0 to R0, then writing this R0 to prime mask. Okay, fault mask is like prime mask, but in this case you can change the current priority level to -1 so that even the hard fault handler is blocked, right? So this is also a special register, and then in this case you can change the priority level to -1 if you want to block hard fault interrupt handler. And the third one, which is basically we are more interested in this prime mask and base PRI. So this will disable interrupts only with priority lower than a certain level. If you set your base PRI to some value, all the interrupts with lower priority will not be executed. So for example, in this case, let's say we are saying our priority level is hex 60. So we will be writing hex 60 to this R0, and then this we will be using MSR to write this R0 to base PRI. So in this case, any interrupts with the priority lower than 96, which means all the priority numbers which are bigger than 96, right? So higher priority means less number, right? So any priority number less than 96 will be executed, but any priority number higher than 96 will not be executed. They will be disabled. So we have looked at these interrupt enable registers, interrupt priority registers, and prime mask and base PRI registers. Now let's look at these functions that we can use to control these registers, and these functions are provided by this CMSIS library. So it will gives us interrupt enable disable functions, interrupt set priority level functions, and interrupt clear pending status functions. So the intrinsic functions are basically the functions in CMSIS that control this prime mask and base PRI. So these are compiler functions, and therefore they use this double underscore. So this is not a user function. Okay, so this enable IRQ and disable IRQ, basically you can set the prime mask. Okay, so basically they are using this ARM instruction. So this is a function, but inside this function actually it is using this assembly instruction, and it is enabling all the interrupts basically. So this disable IRQ, if you go to this CMSIS function definitions, and you will see it is basically using this CPS ID I, right? So this says change processor state interrupt disabled. So this is disabling the interrupts, and instead of using these instructions, so in your C code you can just use this enable and disable IRQ functions. So these are the intrinsic interrupt functions. It means this is specific to processor, and these functions are used to clear the prime mask or to set the prime mask. Basically, if I go to this CMSIS library, you will see these functions are basically using these assembly instructions: change processor state interrupt enable, change processor state interrupt disable, right? So you do not need to understand how it is defined, but just know basically this function is executing this instruction, and this function is executing this instruction. There are also set prime mask functions in the CMSIS library, but it's doing the same thing like this one. it has also set base prime function to set the interrupt level, execution level for our interrupts. So we have some other functions in CMSIS for interrupt control. So we have this NVIC_disable interrupt, and you need to give the interrupt number that you need to disable. So we have this NVIC enable interrupt. You also give the interrupt number, all these functions. So this is for the enabling the interrupts. So if you would like to clear a pending interrupt, then you can use this NVIC clear pending interrupt. And then if you need to set the priority level of an interrupt, then you can do it using this NVIC_set priority. Okay, so you will give the interrupt number and then the priority of the that you want to set for that interrupt. So again, all these are in the data sheets, right, or in the CMSIS library, but there are also get pending and get priority functions. If you need, you can also use them. So what is CMSIS library? So this is a common microcontroller software interface standard. Some people also use Cortex microcontroller software interface standard. So this is basically for Cortex-M. This is a vendor independent library. Okay, as you know, there are different manufacturers of these Cortex-M processors, but this library is vendor independent, so that it will reduce the learning curve, development cost, and time to market of developers, right? So it will improve the software portability and reusability. So you might be getting one microcontroller from TI, Texas Instruments, right? Launchpad, for example. And then if you are using these CMSIS libraries, you can easily port your code to the ST Microelectronics microcontroller. So it is easier for the developers to port their software to the different microcontrollers, and then it improves the reusability, right? But if you are using these library functions, you can reuse your codes in some other projects as well. So there are many more benefits for developing this CMSIS library. And actually what is happening, so you are writing your code here. So you are as a user, you are writing an application code, but by using this CMSIS libraries, then you can access these core peripheral functions or device peripheral functions or the registers easily, and then you can control or modify these registers and whatever you would like to do in your application code. So through these CMSIS libraries, you will be accessing, for example, the processor core, SysTick, timer, NVIC, vector interrupt controller, or debug trace modules, right? So this is like a interface for you in your code that you can access the Cortex-M processor. So this CMSIS library will define register names, address definitions, and it will have some helper functions for you to accessing core registers and core peripherals, and driver codes to access peripherals, right? So it will make your code writing easier, right? And then you can develop fast applications by just using this CMSIS library. So this CMSIS library is publicly developed on GitHub. So if you go to the GitHub, you will see this CMSIS software is already there. So, and then there are different sections in the CMSIS. So we will be basically interested on this Cortex-M core section. So there are lots of documents here that you can look at, all these different sections, Okay, then you can look at the motivation, validation, licensing, and etc. So if you look at the structure of this CMSIS library, there are different sections as we have seen, but we will be mainly working on this for this class. We will be interested in this CMSIS core section. So this CMSIS core is the standardized API for the Cortex-M processor core and peripherals. So if you look at if you go to this core section, then you will see all the include files, documentation related for this core section. You can find it on GitHub as well. So there are many resources here. For example, for the core section, we have this header file. So this is CMSIS Cortex-M4 core peripheral access layer header file. So in this header file, it includes register types and related definitions for all these blocks. And then there are also base addresses and struct definitions for these registers. And also all the function definitions for this NVIC, SysTick, debug, and register access is there. So for example, if you look at this header file in the NVIC type definition, you will see all these registers. So this NVIC has different registers, right? This interrupt set enable register, interrupt clear enable register. So these are all 8 bits interrupt set pending register, interrupt clear pending registers, and etc. So this header file defines the NVIC type as a struct for you. So this header file, we can define this NVIC type registers. So for NVIC, we have different registers here. So they are defined. Similarly, this application PSR type also defined here. So as you see, bits 0 to 16 are reserved, 0 to 15 are reserved. This GE bit field is defined from 16 to 19, and then 20 to 26 is reserved, and then this NZ, CV, and Q flags are defined for these bit positions, right? So, and basically this struct is used for this APSR register. There is also some definitions that makes that if you want you can use them. So this shows the position of the N bit, position of the Z bit, position of the C bit, and mask for each. Bit positions are also defined. So you don't have to use them, but if you like, you can use them. It might make your code writing easier and simpler. Okay, the control register, as well as we have seen this in the previous lecture, we have this privilege bit field and stack pointer select bit field and floating point flag FPGA bit field here, and then some definitions related to this control type. So these are examples for in the header file. So what is included in this header files? So there are also some base addresses for the modules, right? For the SysTick base, for example, the base address for the SysTick is, you just use this CSS system control space base address plus you add this hex 10 to it, and then you add hex 100 for the NVIC base address. Okay, and then these are the pointers for these addresses, right? Then these are also defined. So there are also NVIC functions defined in this header file. So this is the NVIC enable IRQ, and basically it is setting this interrupt set enable register in the NVIC, right? Similarly, you can also disable the interrupt using this NVIC disable function, and it will be going through this register, and then it will be disabling the interrupt number that you specify here. As I said, you do not need to understand the internals or how you define these, but this is already defined for you and then you can just use it. For example, let's say I am trying to enable this USB interrupt. If you look at the data sheet, you will see the interrupt number for USB is 44, and then the enable bit for this USB is actually in interrupt set enable register 1, right? So if you look at the interrupt set enable register 0, it is controlling the interrupt enables for all the bits up to 31. So since we have 44 here for the USB interrupt number, so we will be going to this set enable register 1, and then bit 12 is the location to enable the USB interrupt. So I will be setting this to be 1, right? So if I set this 1, then I will be enabling USB interrupt. So how you can do this? Basically, you can just say NVIC, and we are pointing to this register in the NVIC type register, right? So this is the one of the components of this type, and then we are shifting this bit 1 12 times so that I will be enabling this location. So similarly, if you would like to disable it, you need to use this interrupt clear enable register, and then you will be shifting this bit 1 12 positions, and we will be clearing this bit field. So this is for the disabling, this is for the enabling. Any questions?
Hocam orada nasıl disable yapıyor?
So it will be going to this register, so it will not be changing this register. So this is only for enabling, okay? So you don't change this. So this is the enable register. So there are another register called interrupt clear enable register. It will go to that register, and in that register it will write 1 to that register, not to this one. I haven't shown it here, and it will disable the USB interrupt on that one, okay?
Okay.
So it is using two different registers. One is for the enabling, one is for the disabling, okay? So for enabling you only use this set enable register, but for the disabling you use interrupt clear enable register, which is, I have not shown it here. So this is only set enable register. So this is the enabling section, but this section I only showed the code, I have not shown the register here. We can also use functions to enable and disable interrupt, right? So our first method is just use this NVIC enable IRQ or disable IRQ. Then we will be writing 44 for the USB, right? If you write 44, you will enable the interrupt for the USB. If you write 44 here, you will be disabling the interrupt for USB. So another method is this. So there are more than one register, right, for the interrupt set enable register. So it could be interrupt enable register 0, it could be enable register 1 or 2. So basically, if you put 44 here, right, you will be getting set enable register 1 here. A better solution, instead of doing this, I can just shift it by 5, right? If you put 44 here, and if you shift it to the right 5 times, you will get 1 here, and here, so I have a division operation to find out the register, or I can do a shift operation. So instead of doing a modulo operation, I can also do an AND operation with 1F, and then it will also give me 12 here. So basically if you put 44 and AND it with this 1 hex 1F, you will get 12, which is the same thing as here. So this is a better solution, right? So you can try yourself and verify these two are the same, okay? So this and this is the same, and this operation with this operation is the same, which basically this, right? Here I find myself, this is the interrupt set enable register 1, and I need to shift it by 12, so I did this myself. So because I know this was 44, so I need to, it is the bit 12 of this register, but also you can just use this, and this will give you 12 here and 1 here. And similarly for the disable operation, you can just use the same technique, right? Okay, so let's look at this enable IRQ, and we can enable IRQ function in this header file. If you look at the header file, you will see basically it is doing this operation that we have shown you in the second line, okay? Basically it is doing setting these set enable registers and clear enable registers in this header file. But we can just use this function directly. We don't need to worry about what it is doing here. So we can also set the priority level using this set priority function. So it is setting priority for this interrupt 7, and the priority level is setting it to be 6. Okay, basically you are writing 0 1 1 0 here, and you are not using this section. So in the register basically you will be writing 96, okay, because you are writing 6 but you are using the 4 most significant bits. So this will be hex 96 here. Another way of doing this is you go to interrupt priority register 7 and you put 6 to it. And then to put 6, you need to shift it by 4 times, right? Because we are not using the first 4 bits. So you can shift it by 4 and you will get this number. And then why we need to do this, end it with 0xFF, because this is 32 bits, but we are only getting 8 of these bits, right? Because this register is 8 bits, right? So this is the 8-bit register. So that's why I need to end it with hex FF, because I am only interested in the first 8 bits. But this operation is done on 32 bits. So you can also look at this NVIC set priority in this header file. Okay, in this header file, it is basically saying it is looking at this number. If it is an exception, it is doing something else. Right, but if it is not an exception, then it is using this interrupt priority register, and it is setting it accordingly. So we can also use this double_set base PRI function to disable all the interrupts with less urgency. So for example, if I would like to disable interrupts with priority value same or higher, then I can say if the interrupt number is less than 5, it will be executed. If it is higher than that, it will not be executed. I am shifting it by 4 because this is also 8-bit register and the 4 bits are not used. Okay, so to remove the base PRR masking, I can make it 0, so all the interrupt requests will be executed if you make it 0. So to summarize the interrupt process, we first need to enable the source interrupt, right? So for this we need to go to this NVIC enable register. So this could be 0, 1, 2, 3. But for SysTick, we can just do the enabling in this SysTick control register, right? So to set the priority, we need to use this NVIC priority register. So this could be 0, 1, 2, 3, 4, 5, 6, 7 or whatever, right? So we have seen which register controls which interrupts. Then we need to enable all the interrupts in the assembly code or in the C code. In the interrupt service routine, what we need to do, we need to clear the flag that requests the interrupt, right? But in SysTick, ISR does it automatically, so you don't need to worry about that. And then we also need to do push and pop operations if these registers are used, right? We have seen this push and pop operation in the last lecture. So let's look at a SysTick interrupt example. So we have our main function. We are initializing our PLL. We are initializing our port F. So this is using SysTick init to switch the pins in port F. And then we are initializing our SysTick timer such that the SysTick timer will generate an interrupt every 1 milliseconds. Okay. So if you go to SysTick initialization, we are putting this period to be 80,000 here so that we will be getting this 1 millisecond. So we are writing the current R to be 0. And then now, since we are using this SysTick interrupt, we need to define the priority. So this SysTick is defined in this priority 3 register. Then we are reading this register and then we are setting the bits 31 to 29, which controls the SysTick of this register. Okay, if I go to this register and then these bit fields, it defines the priority of the SysTick. So I am saying the priority of the SysTick is 4, and then I am enabling my SysTick here, right? After the initialization, I am enabling all the interrupts. This is the global enable, and this is my code, the while loop. And then, so every 1 millisecond, there will be a SysTick interrupt. And then once there's an interrupt, I will be executing this. So note that I am not clearing the flag here, right? The SysTick, it is done automatically, so you don't have to worry about the clearing the flag for the SysTick. So we can also have an interrupt from our GPIO pins. So there are some registers that controls the interrupt for the GPIO. So this is the interrupt sense register, determines level or edge triggered. So if this, so this X is could be A, B, C, E, F, right? If it is 0, so this is a edge triggered interrupt. If this is set to be 1, it is a level sensitive, right? It is not looking the edges, but it is looking at the whether the voltage level is high or low. This is level sensitive. So this interrupt both edges register. It just tells us whether if there is an edge interrupt, it is on the both edges or not. If it is 1, it means the both edges are used for the interrupt request. If it is 0, it means interrupt is controlled by this interrupt event register. So this interrupt event register, if it is 0, it means the falling edge will be used for the interrupt request. If it is 1, rising edge will trigger an interrupt. So interrupt mask register, if it is 0, it is disabled. If it is 1, it is enabled. And then interrupt clear register, it clears an edge triggered interrupt, right? If you write 1 to this, the interrupt is cleared. So let's see an example. So this is an port F edge triggered interrupt enable. So this is we are enabling the clock here. We are unlocking here using this commit register. So this line configures port F0 to port F4 as general IO port. We have no analog. and no alternate function here, right? And we are only setting it for the interrupt. So we are setting the ports, digital enables, pull up, registers, and the directions. So these are all our initialization, and from this register then we start using the interrupt processing. So we are saying interrupt both edges. It's saying 1 1, it says not both edges. We are actually looking at PF0 and PF4. Okay, it's saying we are not using both edges, but we will be using only the falling edge as an interrupt request. Before we start, we clear the interrupt flags before starting using this ICR register, and then we enable the external interrupts on PF0 and PF4 in this mask register. And here we are setting the priority, and this priority for port F is in this register, and then we are setting its priority to be 4, but you are writing 8, but basically you are setting the priority 4. Okay, if you go and check this register bit fields, basically it is only using 3 bits, and it is written 8 here, but actually it is 4 in the register on that bit field if you look at the bit field. And finally, we need to enable the register in the NVIC register, right? So the bit field 30 is made 1 here. Why? Because the port F interrupt request number is 30, and it is the bit 30 in the enable 0 register.